Okay, this is Math 1090. I'm your instructor, Jason Underdown, and in this video we're going to cover section 1.1 on functions. Let's start with definitions. A function is a relationship between two quantities where every input has exactly one output. The domain is the set of all the inputs of a function, and the range is the set of all the outputs of a function. So a function is a relationship between values in the domain and values in the range, such that every single value in the domain gets mapped or related to exactly one value in the range. We have four ways to represent functions. We have function notation. We can use a table. We often use graphs and formulas or equations. So I have an example here of function notation. I've written P is equal to f of n. So that's not multiplication there. That's our new function notation, and we read it as f of n. And what we're doing here in this equation is we're defining a new function. We don't typically call this an equation, because what we're doing is we're just naming the expression. And the expression is how we define the function. So we're defining f of n to be given by the expression 1/3 n plus 2. So it's kind of interesting. We have three different names here. We have p and f and n. So f is the name of the function. N is the symbol or variable we use to represent input values, and P is the symbol or variable we use to represent output values. Now you should also be aware that it's common to kind of abuse this notation slightly, and instead of writing P is equal to F of N, sometimes we don't want to bother with giving a name to a function, and so we'll just write P of N. And what that means is we're just saying P is dependent on n. You need to have a value for n in order to get a value for p, but we're just not giving the function a name because we don't want to bother with that. So you'll occasionally see this notation P of n as well. Okay, also in case 4, when we use a formula or equation, you might see something like what we have here, 3p minus n equals 6. And then if we solve that for p, we find that p is equal to 1/3 n plus 2, or the same function we had up above. But notice that we don't need to give an explicit name to the relationship between p and n necessarily. Okay, so an equation is one way to define a function without giving it an explicit name. And this is common. We don't often want to waste time trying to name things, because naming things can be difficult. Okay, so here's an exercise. Consider the quantity Q of drinks sold at Fizz every hour can be described by a function of the temperature during that hour, T, and is given by the equation Q is equal to 2.5 T plus 45. So here, this equation is establishing a relationship between an input variable T for temperature and the output variable Q for quantity sold every hour. So we can use this to answer some questions. Part A, how many drinks will be sold when the temperature is 90 degrees Fahrenheit? What we want to do here is evaluate this function for the quantity when the temperature is 90. Okay, so we need to evaluate for Q. 2.5 times 90, well, that's 2 times 90 plus half of 90. 2 times 90 is 180. Half of 90 is 45. 180 plus 45 is 225. And let's see, 225 plus 45, that is 270. Okay, so we would expect to sell 270 drinks every hour when the temperature is 90 degrees Fahrenheit outside. Part B, how many drinks will be sold when the temperature is 106 degrees Fahrenheit? Again, we want to evaluate this function when the input is 106. I'm going to use my same trick. 2 times 106 is 212. Half of 106 is 53. 212 plus 53 is 265. So the quantity will be 265 plus 45. Oops. 45, and that is 260 plus 40 is 300, plus the 2 5s is 310. So we would expect to sell 310 drinks every hour when the temperature is 106 degrees Fahrenheit. How about part C? How hot would it have to be to sell 300 drinks in an hour? Okay, so this is a different kind of question. Here, instead of being given the temperature and asking for quantity, we're given the quantity, Q, and we're being asked to get the temperature. So what we want to do is we know the quantity. We know the quantity is 300 drinks every hour. So we want to set up this equation. 300 is equal to 2.5 T plus 45. We know Q and we want to solve for T. Okay, so we can solve this equation by subtracting 45 from both sides, and we get 255 is equal to 2.5 T. And now I divide both sides of the equation by 2.5, and I get T is equal to 255 divided by 2.5. I can't do that in my head easily, so I'm going to use the calculator. Let's see, 255 divided by 2.5 is 102. So T is equal to 102. Hold on here, let me fix that a little bit. 102. All right. Okay, let's continue on. Sandbar SLC is going to buy commemorative t-shirts to give to its customers according to the following function. So here we have a graphical representation of a function, don't we? The horizontal axis of our graph, is the set of inputs to the function, and the y-axis represents the outputs of the function. So the inputs are quantity ordered, and then the outputs are going to be the total price for the order. Okay, so let's answer these questions now. How much will it cost to order 100 shirts? So what we're given is the quantity. So that's a value on the x-axis here, the quantity. And we're told for 100. So let's see here. That would be this point right there. If we're going to order 100 shirts, now we go over to the y-axis and we see that it corresponds with $400. So it's going to cost us 400. It doesn't say what unit of money it's using, does it? So we'll just leave the units off. We'll just say 400. Okay, how much to order 300 shirts? Okay, so we know the quantity again. So our quantity is 300. So we go up to the graph and we get this point, and we see that it's related to a cost of 700. Okay, so it's going to cost, yeah, it's going to cost more to order more shirts. That makes sense. Part C. How much are the setup costs if no shirts are ordered? So no shirts, that's 0 shirts. Our quantity is 0. So that would be, I'll use red for that one. That would be here, and that would be this point on the graph. It's the y-intercept, isn't it? Looks like 250 to me. Okay, so it's going to cost $250 just for the setup to print the shirts. So, yeah, a setup cost. Sometimes it costs money just to set up the silk screening or whatever process you're using to make the shirts. The profit in thousands of dollars for selling bins of cat food in thousands is given by the function p of x is equal to negative 2x squared plus 260x minus 7200. For what numbers of bins of cat food is the company making a profit? All right. So let's see. The input to this function is bins of cat food. So the x-axis is going to represent how many bins of cat food we sell in thousands. And then the output is going to be the profit in thousands of dollars. Okay, so it's important to recognize that the number of bins of cat food is given to us in thousands, and then the profit is also measured in thousands. So part A, for what number of bins of cat food is the company making a profit? Well, you're making a profit when your profit is greater than 0, right? So this x-axis on this graph represents quantity, the y-axis represents profit. So everything, let's see, everything in this region of the x-axis represents a profit because the profit values are all positive in that region, whereas anything in this region or this region is going to be negative profits, which is no good. So let's see here. For what numbers of bins of cat food is the company making a profit? So kind of covered over the numbers, but let's see. It looks to me like this would be 40,000, and over here would be 90,000. So I think we could see here for part A. Okay, so for what numbers of bins of cat food is the company making a profit? It's going to be between 40,000, 40K, and 90K. For what number of bins of cat food is the company losing money? That would be so anywhere from 0 to 40K or from 90 and up above. So that would be 0 to 40K, and then also on the interval from 90K on up, and we'll take the union of those two sets. What is the profit for selling 60,000 bins of cat food? Okay, I'm going to make this a little smaller now. 60,000 bins of cat food. So that's this line right here. And that puts me right there, which corresponds with a profit of $1,200,000. So that's going to be 1,200 times 1,000. Just tack on 3 zeros, put the commas in, and there we go. The profit when we sell 60,000 bins of cat food is going to be $1.2 million. All right. Okay. Let's continue on. Note, not all graphs represent functions. For a graph to represent a function, it must pass the vertical line test. What is the vertical line test? The vertical line test. If any vertical line intersects a graph more than once, then the graph does not represent a function. Okay, so which of the following graphs represent functions? Well, clearly I can draw vertical lines on this graph, and they only intersect the graph in one location, in one point. So this is a function. So, yep, this one's good. This one also, if I draw vertical lines on the graph, every single vertical line intersects the graph in just one place. So that is a function as well. Let's move on. Okay, now notice with these graphs, when I draw a vertical line on these graphs, I intersect the graph in more than one point. So these are not functions. Okay. Why are they not functions? Well, think of it this way. This point right here, somewhere between 1 and 2, it looks like maybe 1.6. The value 1.6 is getting related to both this value, something a little below 2, and this value on the y-axis, something between -1 and -2. So the x value is getting related to multiple y values, so that's not a function. That's why the vertical line test helps us determine whether a graph represents a function. Okay, how about which of the following tables represent y as a function of x? Well, we have to make sure that every input is related to exactly one output. Now in this first table, since every single input just occurs once, every single input is being related to exactly one output. Same with this second table. Okay, so notice that 7 is getting related to 6 and 12 is getting related to 6. So we have a repeat in our y values, but that doesn't matter because 1 is only being mapped to 5, 7 is only being mapped to 6, and 12 is only being mapped to 6. So this is a function. So these first two tables are functions. How about this third one? Well, here we have a problem because 7 is getting related to 6, but 7 is also getting related to 15. That is not a function. So yeah, that's not a function. Okay, some more definitions here. So these are actually, I think, from section 1.6 of your textbook, but we want to use some of these ideas, so we're going to move these up ahead into the first video. So interest is money paid regularly at a particular rate for the use of money lent, or for delaying the repayment of a debt. That's interest. Principal. Principal is the initial amount borrowed or lent that must be paid back. Okay, so the principal of a loan. The supply curve is a graphic representation of the relationship between the price of a good or service on the y-axis and the quantity supplied on the x-axis. Okay, so a graphic representation between price and quantity is the supply curve. A demand curve is a graph depicting the relationship between the price of a good or service on the y-axis and the quantity demanded at that price, the x-axis. So that's the demand curve. Okay, a few more definitions. Equilibrium price. This is the market price where the quantity of goods supplied is equal to the quantity of goods demanded. So this is where supply equals, this is the price at which supply equals demand. That's the equilibrium price. We also have equilibrium quantity. The quantity that exists when a market is in equilibrium. Equilibrium quantity is simultaneously equal to both the quantity demanded and quantity supplied. In a market graph, the equilibrium quantity is found at the intersection of the demand curve and the supply curve. A few more definitions here. We have a cost function, often written as C is a function of Q, where Q is quantity, expresses the production costs in terms of the amount of items produced, Q, or the quantity. A revenue function, R of Q, is the product of the price per unit times the number of units sold. So revenue is always going to equal the price times the quantity. And then the profit function, P of Q, is the relationship between a company's total profit and output. It equals total revenue minus total costs. Okay, so these are kind of the important things to remember for these functions. Revenue is just price times quantity, and profit is revenue minus cost. Okay, let's move on here. Let's do another exercise. Sherry takes out a 25-year mortgage for which her monthly payment is $1,400. Oh, that's a typo there. During the early years of the mortgage, most of each payment goes towards interest and a rather small remainder for the principal of the loan. As time goes on, the portion of each payment that goes for interest decreases, while the portion that goes to the principal increases, as shown in the following graph. So let's take a look at this graph. So on the x-axis here we have time measured in years, and on the y-axis we have dollars, it looks like. Okay, and so how much she's paying towards the principal of the loan and how much she's paying in interest towards the loan. The interest of the loan is represented by these two curves. And the sum of both the red and the blue, you'll see, is a constant value. It looks like, let's see, it's about $1,100 plus $300, which would be about $1,400 she's paying each payment. Yeah, because at the end of 25 years, she's paying $0 in interest and $1,400 in principal. So the entire payment goes towards the principal of the loan on the last payment. Okay, so let's answer these questions. Approximately how much of the $1,400 payment goes for interest in year 5? Let's see, so in year 5, how much goes to interest? That would be about, that's that point. So that looks to be about maybe $980. And it just asks us for approximately, so let's say $980. Part B, in what year will the monthly payment be equally divided between interest and principal? Oh, that's this point right here. And that looks to be about year 13. So, year 13. Part C, during what years will more of the monthly payment go towards the principal? So that would be in this region here. So everything beyond the year 13, more of the payment goes towards the principal. So that would be years 13 to 25. Okay. Next example or exercise. The monthly supply and demand for a particular type of ATV is represented by the accompanying supply and demand graph. The quantity is in thousands and the price is in hundreds. Use the graph to answer the following questions. The demand curve is red and the supply curve is blue. Approximate at what price 5,000 ATVs are supplied. Okay, so we want to use the blue curve, that's the supply curve. And we know the quantity, 5,000, we want to figure out the price. So let's see. So when we supply 5,000, we will supply 5,000 ATVs at a price of $2,000. So $2,000, that's 20 times 100. So that's $2,000. Yeah, $2,000. So the market will supply 5,000 ATVs when the price for an ATV is $2,000. Approximate at what price 5,000 ATVs are demanded. So we want to use the demand curve for this, and when 5,000 ATVs are demanded at a price of about 7,800. So 78 times 100, or $7,800. So 5,000 ATVs will be demanded when the price is $7,800. Okay. Estimate the equilibrium price. Well, the equilibrium price is where the two curves meet. And the price is on the y-axis here, so that would be $6,500. So 6,500. Estimate the equilibrium quantity. That's the value on the x-axis in thousands, so that would be 16,000. Okay, let's look at this next exercise. So you decide to begin selling mood rings at a local fairground. Your cost for each mood ring is $1.93, plus you have to pay a fee of $130 each week for the booth. Your plan is to sell each mood ring for $3.83. Write a cost function to represent your total costs for the week if you sell in mood rings. Okay, so our cost function, the cost as a function of the number of rings sold is going to be the cost to us for each ring, and that's $1.93, so $1.93 in, plus our fixed costs of $130. Oops. There we go. That's our cost function. Write a revenue function, R of N, to represent the revenue from the sale of N mood rings during the week. Well, we're going to sell each mood ring for $3.83. So for every single ring we sell, we're going to take in $3.83. So our revenue function will be 3 3.83 in. Part C, write a profit function, P of n, to represent the profits for selling in mood rings in a given week. Now remember that profit is revenue, money coming in, minus costs. That's money going out. So profit, this is revenues minus the costs, or in this case this is going to be 383N minus, let me just check, it was $1.93. So minus the entire costs, which is 193N plus 130. Okay, let's simplify this. So this is 383N minus 193N, but when we distribute the negative sign, the 130 also becomes negative. Let's see, 383 minus $1.93, what is that? I'm going to use the calculator. So 3.83 minus 1.93 is $1.90. Okay, so this is going to be 1.90 in minus 130, and that's our profit function. Okay, part D. What is the minimum number of mood rings you must sell in order to not lose money? This number is called the break-even point. Okay, so what does N have to be in order for our profits to be between positive and negative? In other words, 0, right? So the break-even point corresponds with your profits equaling 0. That's where you just begin to start making money and you stop losing money. Okay, so what we want to do is set the profit equal to 0. So that's P of n. So 0 is equal to 1.90 times n minus 130. Or in other words, we need to solve 1.9n equals 130. So divide both sides by 1.9 and we get n is equal to 130 divided by 1.9. Okay, what is that? I think I'll use the calculator again. 130 divided by 1.9. It's about 68.42. So n is approximately 68.4. We don't need to be super precise. So we need to sell at least this many rings, so really n has to be greater than or equal to 69 rings. We got to sell at least 69 rings in order to break even. Okay. Suppose a computer manufacturer has the total cost function C of x is equal to 103x plus 12,924 and a total revenue function of 462x. Write a profit function for the computer manufacturer. Okay, profit is just revenue minus costs. So let's see, what is revenue? It's 462x minus the costs. It's important, I got to put the whole expression for my cost function in the parentheses. So 103x plus 12,924. Now we can simplify this. Let's see, 462 minus 103. I can do that in my head. that's 462 minus 100, which is 362, minus 3. 362 minus 3 is 359. So that's going to be 359x minus 12,924. There we go, that's my profit function. What is the profit for 72 units? Okay, we just need to evaluate the profit function when the quantity x is 72. So P of 72, this is going to be 359 times 72 minus 12,924, which is 359 times 72. Calculator time. Let's see, 359 times 72. 25,848. 25,848 minus the 12,924. Okay, yeah, we should probably do that on the calculator. Let's go back to the calculator and subtract the 12,924. So minus 12,924. Is that right? It's exactly half? Let's just check that. 2 times 12,924. Oh yeah, look at that. Okay. So the profit is $12,924 when you sell 72 units. Okay, how many computers must be sold to avoid losing money? This is again the idea of the break-even point. So we want to set the profit function equal to 0 and solve for x. So we want to set, we want to set this function in the box here equal to 0, solve for x. So we need to solve 359x is equal to 12,924. So x is equal to 12,924 divided by 359. I'm going to do that on the calculator as well. So 12,924 divided by 359 is 36. So x equals 36. So we need to sell at least 36 computers to avoid losing money. That's our break-even point. All right. It doesn't say like what time period that is. Is that monthly? Is that daily? It doesn't say, but that's okay. All right. This concludes section 1.1.